Okay, our last activity for this unit is power and efficiency. So power is the amount of work you do in a given amount of time. So power is measured in watts, which is work in joules divided by time in seconds. Now, a famous activity that they do in grade 11 physics is to have people run up the stairs to see what their power is. Now, when we picture a powerful person, we always look at a bigger person, but if we have a bigger person going up the stairs and it takes them a long amount of time, their power rating is not that high. If we have a smaller person going up in a less amount of time, then they can have as much power as the bigger person. Now, if you've got a bigger person and they go up in a short amount of time, then you've got a lot of power that you're generating. So one derivation of this formula that's really important, substitute change in energy for work is equal to power times time. And we'll use this when we're doing energy ratings on appliances in our kitchens. So this can be an important use of this formula. I want you to be aware that work is equal to force times distance. So to get the work to go in this formula, we can use work is equal to force times distance, or work is equal to the final energy minus the initial energy. One thing that's very important when we're looking at power is percent efficiency. So if you take an example of a light bulb, I'm going to go to the old school light bulbs that were incandescent, meaning they operated on heat. What would happen is they would have an electrical energy input going in. Most of that output didn't go towards making light, it went towards making heat. So therefore these light bulbs were only 5% efficient because most of the energy was transformed into heat instead of being transformed into light. When you do these calculations, your smaller number will always be your output. It'll always be on top. Remember to multiply by 100 because it is percent, which means multiply by 100. Remember, there are two ways to find energy. We can either do power times time, or we can take a look at the changes in kinetic energy that occur. Here's an example of an efficiency problem. A 98 kilogram athlete can produce 2,300 watts of power for 5 seconds. During this time, the athlete's 7 kilogram bike accelerates from 5 meters a second to 10 meters per second. So if we want to do the input energy, that's going to be the power that athlete can generate times the time. So it's going to be 2,300 times 5 equals 11,500. The energy output is going to be based on the mass of the bike and the change in velocity. So it's going to be half mv squared minus half mv squared. So it's going to be 10 squared is 100 times the mass. 7 is 700, that's 350 joules. And that's going to be subtracting the initial velocity, which is 5 squared, which is 25. 25 times 7 is 175. So 175 times 0.5 is going to be 87.5 joules. 350 minus 87.5 is going to be 262.5 joules. If you want to take a look at the efficiency of this athlete, it's not going to be very high because the output is going to be 262.5 over the input of 11,500 and multiply that by 100. So 262 divided by 11,500 equals, and times 100 equals, we only have a 2.3% efficiency. So that athlete can generate a lot of energy or power, but not much of that is being transferred into that bike being efficient.